Now let us quickly go through what graphs are. We are not going to go into detail because rest of the other parts of graphs we will try to look in the third unit, fourth unit, I suppose, where we have breadth first and depth first search traversals. Now, this figure, if you look at this figure, if you observe this figure, what is happening is this figure is, okay, if you look at this figure, what you can see is there are certain vertices or some nodes. And those nodes are connected through some lines. Formally, a graph is a set of vertices. You can call it as nodes also, but in terms of, or in graphs terminology, nodes are known as vertices. So graph is a set of vertices. So in this case, we have a set of vertices known as V. We have 4 vertices, 1, 2, 3, 4, and a set of edges, which is E. So a graph is represented using set of vertices V and set of edges E. Each edge contains a pair from one node, from one vertex to another vertex. So if you see this pair 1, 2, so there is an edge between vertex 1 to vertex 2, 1, 3. There is an edge between vertex 1 to vertex 3, 1, 4. Some edge between vertex 1 to vertex 4. So all this within the set of E are known as edges, set of edges. So graph is represented using set of vertices and set of edges. Now if you look at this graph, graphs may have the edges of the graph may have orientations. If the edge doesn't have an orientation, it is known as undirected graph. And the edges of the undirected graph are ordered. So there is an edge between 1 to 3, 1 to 2, 1 to 4. There is no direction, no orientation on that edge. So these edges are known as unordered edges. And a graph with unordered edges is known as undirected graph. Let us look at another scenario. Now everyone will look at this and say that this is a tree. This tree can also be represented as a graph. So we will call it as a tree, but can be represented as a graph, which has a set of vertices V as 1, 2, 3, 4, 5, 6, 7, and set of edges. That is 1 to 2, there is an edge, so 1 to 2. 1 to 3, there is an edge. 2 to 4, there is an edge over here. 2 to 5, there is an edge. 3 to 6, there is an edge. 3 to 7, there is an edge. So this is also a graph, but usually it is called as a tree. Now, is this directed or undirected? It is undirected because there is no orientation for the edges, and edges are unordered. So this graph is basically a tree. Now, why we are calling this as a tree? There's something known as cycle, and we will look at that definition later in these slides. So, but this is called as a tree. Now let us look at this graph. This graph, there's 3 vertices, 1 to 3, and their edges is 1 to 2, there is an edge. Now at this case, you can see that in this example, what we find is, that the edges have some direction. There is an arrow to the edge. When edges has direction, that means edges has orientation. So this graph, or a graph which has orientation or edges which has orientation or direction, then those edges or the graph, the edges are known as ordered edges, and the graph itself is known as a directed graph. So in a directed graph, edges are ordered and there is an orientation or a direction to the edge. Oh, sorry. There. So, when there is a direction to the edge, what this means is there is an edge between 1 to 2, as well as there is an edge between 2 to 1. So the arrow of the edge represent the direction of the arrow represent from edge is going from which vertex to which vertex. So there is a from 1 to 2 there is a edge, from 2 to 1 there is an edge, and then from 2 to 3 there is an edge. So this is known as a directed graph where edges have orientation. The next thing. Now when this the graph on the left side, this is a directed graph because all edges has orientation. And if you observe, there is an edge from vertex 1 to vertex 1 itself. So this edge is known as self-edge or self-loop. This self-edge and self-loop we will not be using or considering. We don't consider. It's not permitted in design and analysis of algorithms because there are various algorithms which may not work if we have a self-loop, and there is no point in having a self-loop. So realistically what we say is it's not legal to have a self-loop. It's not permitted. There is a restriction. So we say there will not be any self-loop. As well as if you look at the graph on the right side, in this graph, you can find that there are multiple occurrences of the edges. Though this is undirected graph, there's no direction, but there's multiple occurrences of the edges. Now, this multiple, and remember, this is undirected graph. If it is directed and one edge is going from 2 to 4, another coming from 4 to 2, that is no problem. That's not a problem. But here, there are multiple edges and the graph is undirected. So, this multiple occurrence of edges from 2 to 4, or even here, the next one, that is 3 to 4. These edges, there are 3 edges from 3 to 4. There is no direction also. These are multiple occurrences of edges. This is also not permitted. This is known as multi-graph. And it's not permitted, is not, used in this course. So we don't consider graphs which have self-loops and graphs which have multiple occurrences when the edges are undirected. So these two things are not permitted, so we will not be using it, and the textbook itself will not consider this. Now let us see another definition in graph terminology, which is known as a complete graph. Now let us look at this graph. We say that this graph is a complete graph. Now in simple sense, a complete graph is a graph in which each vertex is connected with an edge with all other vertices. So if you see vertex 1 is connected, all other vertices are vertex. If you take vertex 1, all other vertices apart from vertex 1 is vertex 2, vertex 3, vertex 4. So vertex 1 is also 2 is also connected with 1, 4 is also connected, 3 also. Same way with 3, vertex 1 is connected, 3 is connected, and 4 is connected. With 4, vertex 2 is connected, 1 is, and 3. So with 3, vertex 1 is connected, 2 is connected, 4 is connected. So if you pick a vertex in a graph, all other vertices apart from that vertex will be connected for every vertex. This is known as a complete graph. Now, mathematically, a graph which has n vertices, if a graph which has n vertices also has n into n minus 2 by 2, n into n minus 1 by 2 edges. A graph with n vertices having n into n minus 1 by 2 edges is known as a complete graph. This is how mathematically we represent graphs. Now there are 4 vertices here, so n is 4. So 4 multiplied by 4 minus 1 is 3. So 4 into 3 is 12. 12 by 2 is 6. You can find that this graph has 6 edges. So any graph with n vertices having n into n minus 1 by 2 edges is known as a complete graph. Then there's some topic known as subgraphs. Now this is a graph. The top one is a graph. Its subgraphs. These are its subgraphs. So how will we define subgraph? A subgraph will have vertices as the subset of the original graph. For example, 1, 2, 3 is there. So here, set of vertices 1, 2, 3, 4. So 1, 2, 3 is a subset of 1, 2, 3, 4. Even here you can check same way. Even this is a subset, there's no problem. Then edges also will be a subset of the edges of this original graph. So subgraphs are nothing but a part of those graphs. So these are the three possible subgraphs. Well, you can have many more subgraphs. Let us take this. Even a single node, vertex 1. It's a subset of vertex 1 to 3. So it's a subgraph. We can have these three vertices connecting 1 to 2. It's a subgraph. Even this is a subgraph. Even this is a subgraph. So subgraph means it's a part of the graph, part of the vertices, part of the edges, sub-edges, sub-vertices. So these are some examples of subgraphs. Now let us look at some more few definitions over here. Now here what we have is, if we have an edge between vertex u to vertex v, some vertex u to vertex v, from vertex u to vertex v, then we say that vertices u and v are adjacent. So in this case, in this left side, 1 and 2 is an edge, so 1 and 2 are, vertices 1 and 2 are adjacent. 3 and 4 is an edge, 3 and 4 is an edge, so vertices 3 and 4 are adjacent. Now what about this graph on the left side? 1 and 2 edge, 1 and 2 is an edge, so they are 1 and 2 are adjacent. 1 and 3, there is no edge between 1 and 3. 1 and 3 is not an edge. So note vertex 1 and vertex 3 are not adjacent vertices. So adjacent vertex means if u and v is an edge, then vertex u and v are adjacent vertices, or they both are adjacent. Then there is another definition known as path. Path is nothing but from vertex u to vertex v, if there is a sequence of vertices such that there is an edge between each pair. So for example, if you consider this graph on the left side, from vertex 1 to vertex 2, there is an edge. From vertex 2 to vertex 4, there is an edge. From vertex 4 to vertex 3, there is an edge. So there is a path between vertex 1 to 2, 2 to 4, 4 to 3. If you consider this graph on the right side, there is an edge between 1 to 2, and from 2 to 3 there is another edge. So there is a path between 1 to 2, 2 to 3. Though in this case 1 to 3 there is direct edge, 1 and 3 are adjacent. But when we say path in this graph, 1 to 2, 2 to 4, 4 to 3 will be a path. In this case there is no direct edge between, on the graph on the right side, direct edge between node 1 to node 3. But there is a path between node 1 to node 3, that is from node 1 to 2, from 2 to 3. So this is what is a path. Now, I told you we'll talk about cycles later. A path in which the first and the last vertex is the same is known as a cycle. So if you look at this case on the graph on the left side, 1 to 2, 2 to 3, 3 to 1. 1 to 2, 2 to 3, 3 to 1. There is a path between 1 to 2, 2 to 3, 3 to 1. So this forms a cycle. Now here in this case, we have a path between 1 to 2, 2 to 1, 1 to 2. This is directed graph, 1 to 2, 2 to 1. So this is a cycle. But in this case, there is no cycle between 1 to 3. Because you can go to 1 to 2, 2 to 3, but from 3 you cannot go again back to 1. So there is a no cycle between 1 to 2, 2 to 3 and 1. But though there is a cycle between 1 to 2. Now, the difference between graph and tree is that graph will have cycles. Graph can have cycles. May or may not. That is also a different issue. But usually graph has cycles. But tree will never have a cycle. tree will never have a cycle. That's the difference between graphs and trees. Now, let us look at another topic or definition or term, connected graph. If we say graph is connected if and only if every pair of distinct vertices, remember, distinct vertices means different u in different v's. For every pair, there is a path from u to v. Now, if you consider this graph on the left side, how many vertices are there? There are 4 vertices, and from every vertex, you can reach every other vertex. That is, between different distinct pair of vertices, there is an edge. So actually, every pair of vertices, there is an edge. Let us consider the graph on the right side. Now here, don't get confused. Just a second. Here, don't get confused. These are not 3 graphs. These 2 things, these 2 subgraphs, no, these ones, these 2 are single graph. There are no different graphs. That is why nodes are numbered from 1, 2, 3, 4, 5, 6, 7, 8. So these 2 are singles graph. So the set of vertices, there are 8 vertices in this graph. Now this graph is not a connected graph because you may have 1 to 3, there is an edge, or there might be a path from 1 to 4 with using 1, 2, 4. But there is no path from 1 to 5, no path from 2 to 8. You can't reach it. So between there is, for every pair, there is no, we do not have a path. So this is known as, this is not a connected graph. This graph is not a connected graph. This, because there is no, at least there should have been an edge between 2 to 6 or 6 to 1 or any other. These are 2 disjoint graphs, what we call it. These are not connected graphs. Now, connected components. We talked about connected graphs. Now let us talk about connected components. Now, suppose if there is an edge between 2 to 6, then this graph is a connected graph. But there is no edge between 2 to 6. So these 2 are disjoint subgraphs, actually. This becomes one connected component, and this becomes another connected component. So what we say is, this graph, the entire graph, has 2 connected components. Let us look at another scenario, or let us look at another graph. Here we have A, B, C and D, E, F and G, and between C and E there is an edge. Now connected components also as connected subgraphs is known as connected components. Here, if this edge in red is removed, then this becomes one connected component, this becomes another connected component. Now, there is an edge known as article. There is a edge which connects between, in a graph, there is an edge which connects between 2 vertices, and removing that vertex will result in 2 connected different connected components. Might be different connected, not only 2 connected components. Then that vertex is known as an articulation point. So in this case, if I remove node C, then there will be 2 connected components. So node C is an articulation point. In the same way, suppose if I remove node E. Node E is an articulation point because removing node E we will have connect 2 connected components. So articulate point is nothing but a vertex whose removal will result in connected components. If I remove node D, am I getting connected components? No. So node D is not an articulation point. Now by connected components. Now what happens is last example we had edge between C to E. If we remove edge C to E, they get two different connected components. But now here what we are having? We have an edge between C to E as well as from A to E. So if I remove this edge, the graph doesn't. We don't have connected components because there is still an edge between A to E, and from this edge we will be able to reach all the vertices on the left component or on the right component. As well as if we remove this A to E edge, we have an edge between C to E. So all the vertices are connected. So this is known as bi-connected components. That is, there are two edges, and two components are connected by those two edges. Removing of one edge, if there was only one edge, removing that edge will result in connected components. But in a bi-connected component, removing these two edges, removing any one edge will not result in connected components. So that is one. But edge between A to E and C to E are known as bi-connected components. Now, nothing. Okay. Now here, let us look at the topic of what we call of how to represent graphs. There are several ways of representing graphs. Actually, there are four different types, four different ways of representing graphs. But in this course, we talk about or concentrate on two ways. That is, one is the adjacency matrix, and the other one is the adjacency list. Adjacency matrix is nothing but an array of n by n. It's a matrix n by n matrix, not an array. It's an n by n matrix, where n is the number of nodes or vertices. In this case, we have 4 vertices, so we will have 4 by 4 matrix, and each row and column, the intersection of row and column will give us an edge between them. So if you look at this one, you have node 1 to 2. So in a row, wherever we have node 1, the cell of node 1 and column 2, we are having 1, which means there is an edge. Wherever we have 0, that means there is no edges. All the diagonal elements of this matrix has zeros because diagonal elements represent self loops, and we have already said that we will not be considering self loops or self edges. So we say all the diagonal elements are 0. So if there is an edge between 1 to 4, then in row 1 and 4th column we have 1. This is for undirected graph. So when we say there is an edge between 1 to 4, there should also be an edge between 4 to 1. So that is why first row, 4th column is 1. 4th row, 1st column is also 1. So this is undirected graph. That is why we have to show that, or we have to represent that when there is an edge between U to V, there is also an edge between V to U. Then the other case is that this is unweighted graph. That is, the edge doesn't have weights. That is why to represent edge we are using 1. So wherever you find 1, that means there is an edge. But suppose if there is a weighted edge, this is a representation of another graph. Suppose if there is an edge, edge has weight. For example, this from 1 to 2, the weight is 2. From 2 to 1, assume that the weight is 4. So what we do is 1 to 2, this is a directed graph. 1 to 2, so row 1, 2nd column, instead of 1, we will have the value as 2. and then 2 to 1. So second row, first column, 2 to 1. Instead of 1, we will have 4 as the value. We will have 4 as the value if the edges are weighted edges. Let us take this example. Now this one is not these are not two different graphs. These are disjoint graphs. This is a single graph. There's two components. So what we have is, we have, since there are 8 vertices here, we have 8 rows and 8 columns. Now the next thing is, the different way of representing is adjacency list. In adjacency list, what we do is, we don't make the entire what do you call array, or as adjacency matrices needs a lot of what we call space in terms of representation. So to reduce the space and all, we use of adjacency list. So adjacency list, we make a head node. There is a list. We make one list as head node. For every vertex, we make that as a list head. Then from node 1, who has an edge? Node 4 has an edge. So we will create a node and assign 4 to that element. Then node 1 also has an edge to node 2. So from node, this is a linked list actually. This is a linked list actually, which contains all the vertices which are adjacent to vertex 1. So node 4 is there, node 2, node 3. So there's a list. For node 2, node 3, node 4, node 1. So this is a list. So each node will have its list. Same way, look at this. Node 1, 2. So node 1 is there. Node 1, 2, 3. Node 1 is there. Node 1 has is adjacent to node 2. So there is only one edge in this vertex in this list. Node 2. Node 2 has an edge to node 3 as well as node 1. So two different nodes. So this is basically a list for each node, and each list contains adjacent nodes. So that is what is all about adjacency list and how graphs are done.